Okay, you're connected again via audio, so that's good.
Is
Can
this
you
a
put your?
better quality?
That actually does sound better. Try putting it on speakerphone.
Yeah, it is.
Okay, great. You could probably just set the phone down in front of you, and you should be good to go.
Okay, how about that?
That actually comes in a lot more clearly.
Okay, good. Well, I'll
But
just leave it right there. And
yeah, I don't know if your if your laptop microphone is, or if your laptop is older, or if it has to do with the room you're sitting in, but there was a little bit of a distortion kind of sound to it, and it was making some
okay,
of what you were saying unclear to hear. But now I hear you loud and clear, and you should
okay,
be fine.
good. Let's
So as
try
long
that.
as as long as your phone is plugged in, and it's sitting next to you, you should be fine.
Okay, good.
And worst
Um,
case scenario, if your phone disconnects or something goofy during the session, I can go on microphone and let attendees know that we're just working through some technical difficulties, and then you can just call in and
okay,
get back. But
okay,
that will likely be rare if it happens at all.
okay, good.
Well, good, good. Gosh, we haven't had the opportunity to meet before. So
No, I don't.
I think you did a test session with Megan Furl, our
Right.
education coordinator. I'm the education and events manager, and my primary role at IFAI is actually for our annual expo. I don't generally dive into the geosynthetics world at all, except when they
Okay.
need me, like this week. So um, I am basically here just to hang out in the background in the event that you have any technical issues or questions. I don't intend to say or do anything except press start when the time comes and click end when the time comes.
Okay.
So you
Now,
have 90 minutes starting at 10 a.m. Central, and I guess you're on
yeah,
Pacific time, so 8 a.m.
right.
8 a.m. Pacific. I see you've got your coffee, so you're well
Yeah,
prepared.
yeah. I've
Um,
got a couple cups here, so I'm ready.
oh, good. Do you have any questions about the presentation process or the controls or anything like that?
Well, what happens to this control system that's over here, the one that I used for the phone call? What happens to all of that during the when I'm showing my slides
Yeah,
and
so
talking?
actually it's transparent. It does not appear to anyone watching the session. So while you can see
Okay.
it on top of your slides right now, I assume
Hmm.
uh, I cannot see it, and neither can anyone else
Okay.
watching. So
Okay. And I don't know if are there any questions or anything? That was all kind of rushed during that training thing, Megan. And so I'm really not sure about all these things, but maybe there's
right.
nothing there I need to worry about.
Yeah, there generally isn't anything that you would need to worry about. Um, since we're connected to audio, since your video is showing and since your slides are showing, uh, the only thing that you would really need uh, to concern yourself with is the questions box, which is all the way at the
Oh,
bottom of your webinar control panel. And I one thing that I can do for you during the presentation, if you prefer, is I can monitor the questions.
okay.
And a lot of times what I do when I help run these presentations is when we get to the Q&A section, I'll read the questions out to the presenter to answer.
Okay.
Um, I'm happy to do that if you prefer. Otherwise, if you want to try to watch it yourself during the presentation, you can read them and address them yourself. But that's up to you.
Yeah, I think I would be more comfortable if I've got breaks at certain convenient times
Okay,
uh, where I ask for questions.
sure.
And so I hope that they're not real long ones and complicated ones because already kind of pushing the time a little.
Okay,
So, but I've made an effort of leaving my email address, and so maybe at the end of the thing we can just remind them that if they didn't get their question answered, I'd be happy to try to answer it
Sure.
later.
So then, just for clarification's sake, can I take that to mean when you get to the breaks where you want to address questions that you'd like me to read any questions that we have?
Yeah, there's a sign, I've got a slide that says questions with question marks and so on.
Perfect.
So
Perfect.
I think it'll be obvious when we get to those points.
Yeah. And of course, I'll be here.
Are.
Yeah, I'll be here listening in and paying attention. So I'll make sure that I am watching your cues as far as that's concerned.
Okay, good.
Well, good. I feel good. We're set up. Your video's on, your slides are on, your audio is now coming in. So we should be in decent shape. We've now got about 15 minutes. So I think what we'll start at, we'll start right at the hour on 8, and then you have 90 minutes. So you'll go till 9:30 your time. Let's see. Well, there isn't really, I guess, anything else to say here. It looks like your PowerPoint slides are also attached to the control panel for attendees to download, which is good.
Okay.
Do you have? Go ahead.
There was another question about the handout notes that I sent to Barbara 3 or 4 weeks ago. I was wondering where those show up.
Yeah, those you should have access to it as well. I think in the control panel, toward the bottom there is a menu that's just called handouts. And
I see.
Yep, in that menu is a PDF version of your slides, and anyone who wants them can just click on it to download it or open it up and follow along.
Okay, the one that shows here are geosynthetics and erosion Sprague handout.
That doesn't sound like it's
more.
That doesn't sound like it's yours.
Oh, it might be right below it.
Oh no, wait! It says geosynthetics and erosion Sprague handouts _ Holtz. Is that right? Hold on.
Wow, that's.
Let me open this. Thank you for pointing that out, because I'm not 100% sure that's right, and I can fix that. Let me look. That sounds like the slides from one of our other presenters, Joel Sprague.
Yeah.
Let's see.
Yeah. I know Joel. I've known him for a long time. He's an old timer in this. Maybe not quite as old as I am, but he's been around.
Yeah, I've had him on a couple of different sessions already. Yeah, these are not your slides. Okay, so here's what I will do. I can change that in just a split second here. I just need to go into our files and let's see, events, Geosynthetics 2021.
It should have the same title as the training lecture.
Yeah, training lecture.
Reinforced embankments.
Holtz, here we go. Handouts, that's what I'm looking for. This is reinforced embankments. Let me just make sure this is the correct one. Oh, this is like a 63-page.
Right, exactly. It's fairly
guide from the Department of Transportation.
Right, that's it.
The Geosynthetic Design and Construction Guidelines Reference Manual.
Right, chapter 7.
Okay.
Yeah.
So that's what you want in here?
Yeah.
Okay. So let's go ahead and get rid of Joel's PowerPoint.
Okay.
That doesn't need to be in here at all. All right, drag and drop a file. Okay, so that should be uploading. Okay. Did it change? Yeah. Okay.
Yeah,
what I don't have is a copy of your PowerPoint slides. I don't know if it was your intention to put those in here as a handout or not anyway.
I could. I usually just let people know if they want them, they can let me know.
Okay,
and
that's
I'd be
fine.
happy to send them to them. So
totally
why don't we
fine.
just leave it like that? It'll just be easier right now.
Sounds good. Okay. Well, so here's what I'm going to do since we have 10 minutes to spare now. I'm going to go refresh my beverage.
Okay.
and grab a snack because once you start going, I'll obviously be muted and I'll have some breakfast here.
Okay.
But I'll pop back on microphone in about 5 or 6 minutes, like 3 minutes before we're supposed to start, and just make sure everything is still good to go.
Okay. Good.
Cool.
Thanks
All
so
right.
much, Aaron. Appreciate
No
it.
problem.
Appreciate your
See you in
help.
a few minutes. No problem at all.
Okay. I hope we're still connected. Hello?
We're still connected.
Okay, good. I
Yep.
was the phone kind of went blank, and I thought, oh my.
Oh yeah,
So,
yeah. It'll probably go back into the screen will turn off after a certain amount of time, but
okay, good.
we're still
So,
connected. If for whatever reason your audio cuts out, I'll get on microphone and uh try to politely interrupt you to let you know.
okay, no problem. No problem at
All
all.
right. Well, my beverage is reloaded, so
Okay,
I feel prepared to face the rest of the day.
good.
It's I always have to remember that these events that start early in the day are never particularly geared towards folks on the West Coast. Now we've got
Well,
international participants who are up at like 3 in the morning, but we had a half day workshop last week that started at 8 a.m. 8 a.m. Eastern time. So I was
oh
on the
wow,
computer. I'm on Central time, so I was on the computer running
yeah,
it at like 6:30 Central time, and then the folks
yeah,
on the West Coast were just cursing themselves because it was I think 5 in the morning is when it started. It's pretty
yeah. I did a.
it's pretty impressive for anyone who can get up that early and do a presentation.
It was a chore. The Transportation Research Board had the geosynthetic session, couple sessions on roads, and I was the lead-off speaker at 7 in the morning here. It was
Wow.
10 back east, and I thought, oh, the bloody Easterners, they have no mercy for us on the West Coast.
I know. I'm wondering if you were one of those professors who scheduled his classes for 8 in the morning, because I had a few of those.
No, I tried to have them later, to start later, never
Uh,
earlier than
I had
8:30
a
or
you know,
9:30.
I had a German professor who was like German language class professor who was
Mhm.
absolutely certain that you must wake up and be fresh in the morning and eat a good breakfast and come to class at 7:30 4 days a week. And
Woo!
it reminded me why I never liked that class.
Yeah, yeah, that's a terrible schedule for especially undergraduates. They're
No
up all
kidding.
night.
No
I
kidding.
can
Yeah, there were a few
imagine.
days where I was, up super late, like writing a paper or something, and then I'd think, oh man,
Yeah,
German class, 3 hours.
yeah,
If I go to sleep now, I'll probably oversleep, so maybe I should just stay awake.
that's right. Yeah, and these are your choices. And it's pretty awful, I think, to
Right, right.
put people through that and then expect them to be at their best. That's
No
hard.
kidding.
Yeah, yeah. I don't miss those early morning starts very often. And now, especially that we're not flying, I usually have
Right.
early flights a lot of times, especially if I'm in a meeting in the Midwest or on the East, and you got to leave here early and leave home 2 hours early or 2.5 hours early and so on. And boy, I don't miss those at all. I think these video calls and video conferences are fine.
Right, right, right. I've definitely gotten used to them. And working from home has been, at first I felt kind of trapped at home, but now I'm thinking like, oh, I don't have to make daycare runs. I don't have to fight
Yeah,
traffic. I don't have to do any of that. So as far
yeah,
as I'm concerned, if I'm working from home permanently, I think I'll be all right.
yeah. My son-in-law loves it. He lives in Ireland, and he said, I don't
Ah,
have the commute. I don't have any of the problems. And even though it's a relatively small city.
sure, sure.
Still took him a half hour, 45 minutes to get to work every day. He said, I don't miss that at all.
Yeah. All right, we are right on the hour here. So if you are good to go, I will go ahead and get this launched. Um,
Okay,
you'll hear that wonderful recorded voice talking for a few seconds, saying that the broadcast has
okay.
started. And then if you want to just like count to 3 before you start talking to make sure that uh, your welcome doesn't get cut off. The recording takes like 2 or 3 seconds to kick in once I start the broadcast. So
Okay, and then the slides they should be under this photograph or under the screen, I'm assuming.
yeah, actually, we didn't even think about that. Try advancing your slides once or twice so we can just make sure that everything is working appropriately. You can move that control panel to another window if you want. You don't necessarily even need to worry about it. Um,
Okay. Okay, where is this? Oh, here we go.
Yeah, the important thing is that you can see and move your slides.
No, I don't see mine at all.
You don't see your slides?
No.
Well, that's fascinating. Okay, what did we do? I can see them for what that's worth. Let's see.
Oh, okay. Oh.
Let me try one other thing here. That's okay. We can. I'm going to make myself the presenter real quick, and then I'm going to hand it back to you.
Okay.
Did you get the pop-up that asked you to share your screen?
Yeah, show my screen.
Yep.
Click it.
Yep. Okay, now I can see your slides again. Can you see them?
No, no, I don't.
Where is your PowerPoint window?
It's somewhere under this screen, the white the band here. I don't know where it is. It was showing.
Okay, I'm going to try something else here real quick, if you don't mind.
No.
Go ahead and click yes. I just requested
Okay,
mouse
give
and keyboard
controls.
control. Yep.
Okay. Oh, there they are. Okay, good.
You can see the slides now?
Yeah.
Okay, so now I'm going to go ahead and let's see. If you right click, what happened?
My picture just showed up now and obliterated things. Oh, there it is. Right click it, right?
Yeah.
Yeah.
Okay, so can you see your slides now?
Yep. And they advanced and everything, so it's fine.
Okay, so what I
Good.
need to do then is I do not want mouse and keyboard control anymore. So let's see. Okay, hold on. I'm just gonna. Okay, it looks like you have control here. Presenter has control. Okay, I'm gonna go ahead and click start. Okay, take it away, Bob.
Okay, I haven't heard the voice of the lady introducing things, but
I didn't
I
either,
assume it's
but
okay.
yeah, all the attendees
Okay.
are filing in, so you're good to go.
Okay, good. Thank you very much, Aaron, and good morning, everyone. Welcome to the training lecture. I think it's the only one at this conference, and we have an hour and a half to try to go into some detail and at least give you the background for reinforced embankments on soft foundations, where the reinforcement is our geosynthetics. So I've given this at several conferences. The handout notes that you have are Chapter 7 of the Federal Highway Administration Design and Construction Guideline, written by Ryan Berg and Barry Christopher and myself. Now it's 12 years old, but it's still pretty topical. Not much has happened in this particular aspect of reinforced embankments. Most of the recent developments have been in additional ground improvement or soil improvement technologies. The next slide shows the cover of the manual, and as I mentioned here, let me back up, it is available, the entire manual, 592 lovely pages, are available as a PDF download free from the Federal Highway Administration website, part of your tax money at work. So what we're going to do this next hour and a half, or at least how much of it's left, we're going to outline conventional solutions to embankments on very soft foundations, geosynthetics applications, and case histories. And those are important. They're early case histories, but they're important because we learned how to avoid failure and how to design. And so that's an important part of the background for this. You sound like, well, that's kind of old and all that. Yeah, but they were important lessons learned from those failures. We're fortunate that one highway department and the U.S. Army Corps of Engineers told us what they did wrong. And so we can learn from those errors, those failures, those mistakes, and we've learned how to design and construct these systems. We'll spend a few minutes on design itself, on the concepts and some design details. I'll mainly refer to that chapter 7 for additional information because there's a lot of information, a lot of details in there on design. We'll talk a little, very briefly about soil properties. I'm going to assume that you have access to or know a lot about basic soil mechanics, soil properties. Spend most of our time on geosynthetics, since this is a geosynthetics conference, on geosynthetics testing. And finally, in the last, I'm hoping about 25 or 30 minutes to have time to go through construction procedures for these systems. It's absolutely a critical step. You can have all the fanciest design in the world, but if you don't build it right, it won't work. And this is really critical to these design and construction, successful construction of these systems. We're talking about soft sites that you probably can't walk on, tidal estuaries, dredged retention disposal sites, very recent glacial deposits, and so on. They're all over the world. There are these very soft sites that somebody wants to build something across. When you start, if you're going to build an embankment, you start getting construction equipment out there. Highway contractors' equipment typically is rather heavy, and it gets bogged down. And even here in the upper right, a working table has been installed, and still this rather modest dump truck is having trouble traversing the site. That means the subgrade's failing. And even this small tractor down here has fallen, has sunk into this mud. So what did people do historically? Well, in colonial North America, corduroy roads were quite common. And the last one that I can find was actually constructed in upstate New York, 1927. They cut the trees down, laid them out transverse to the center line. Center line would be right along here. Take the limbs off. You can see all the limbs over here on the side. Built the embankment, and it worked beautifully. These timber logs or the bamboo poles in Southeast Asia all work to distribute the load, to spread the load, and reduce the stress on the foundation. Contractors use timber log or timber mats to walk equipment across soft sites, and plank roads have been used. So conventional solutions are listed here. You can build a bridge. Now, sometimes that doesn't work. If you want to retain dredged spoils, a bridge won't work. Plus, bridges are expensive. Berms and or flatter slopes. That's often the case in highway engineering. The first thing engineers try to do is to flatten the slope or use berms for an embankment in a soft site. That means you got to have right-of-way, lightweight fill, geofoam, expanded clay, glass, lightweight glass materials. Those are all possibilities. Up here in this part of the world, in the Pacific Northwest, sawdust and wood chips have been used for a long time to reduce the weight of the embankment on the foundation. Embankment piles are very common. I guess what they call now pile-supported embankments. Embankment piles were used in Sweden for probably 50 years or 60 years for approach embankments to bridges and for support of railways and highways across soft sites. Excavation and displacement or with replacement of the with high quality granular fill is all a tried and true method. It's been around since the early days of highway construction in this country. Preload or surcharge with or without drains, that works fine if you can support the working table so that you can install the drains. That may require reinforcing. I put in these 3 other items here. A few years ago, I prepared an NCHRP synthesis of highway practice for soft ground, and I could find a paper somewhere in the world that somebody had done grouting or electrical osmosis and claimed that it was economical. I have a hard time imagining it's going to be, but I put it in there in the list just for completeness. And vibro replacement stone columns and vibro concrete column sand composure piles from Japan and so on are all in this kind of geopiers are all in this vibro replacement system. And finally, reinforcement. And today, usually geosynthetics is what we're going to use. Applications of geosynthetic reinforced embankments for new embankments, embankment widening, and for temporary construction access roads. Sometimes to even start the construction, you have to reinforce your access road. And then over local anomalies like sinkholes and underground mines. A couple of slides of just showing some new construction of an embankment across the soft site. You can see separator geotextile. Here's a geogrid, another layer of geogrids, and then completing the construction here in the background. Railways, if they're widening to go from a single to a double track system, can use geosynthetics very effectively under the new construction. You can see here the geosynthetic, the fill has been put in, and they're ready to lay the track. So what's the purpose of the reinforcement? Well, it's to prevent instability. There's a little evidence that we may reduce excess vertical and horizontal deformation, but mostly it's to prevent instability. If you don't have a stability problem, you probably don't need a geosynthetic. Geosynthetics that are used are geotextiles. That's the granddaddy of all the reinforcing systems. Geogrids have been used in the last 25 or 30 years, and PVD drains for foundation soil improvement. And also in there are a lot of geotextile systems like geosynthetic encased columns and so on that kind of would be in this foundation soil improvement technology list. Can you design with geosynthetics? Well, that's what we're going to look at now. The case histories that I talked about earlier and the lessons learned. So the first one I have is the U.S. Army Corps of Engineers retention site in Swan Island, Mississippi. And you can see the start of the construction here. They're rolling out geotextile. They use a fairly heavyweight needle punch non-woven. You can see some instrumentation and inclinometer tubes. Since this was an early project, they spent some money on the instrumentation. But unfortunately, it didn't work real well, and got some cracks and failures. And then they went and looked. Here was the original design, and here in the upper. It was only 11 feet high, 10 feet wide at the crest, and had one layer of this non-woven geotextile in the base of the embankment. And when they went to investigate the failure, stuck a settlement gauge down the pipe that they'd put in the under the embankment, and it was broken. There were two places that they could not extend the probe. And they dug down, and they found the geotextile had merely stretched. It hadn't ruptured. So what was the lesson? Well, you've got to have a strong enough, a high modulus material that's not just going to stretch. And you can do some calculations and figure out what the strain is in that geotextile going across the base of the embankment. And it won't take very much strain. This goes down about a foot, and you have a large settlement here. That's enough to crack the embankment. Here's another case from the coastal west of Virginia. The Department of Highways was rebuilding this bridge up here. Had this kind of tidal flat area here. You can see the construction. Here's the geotextile. This was back in the early days. They really didn't stretch this out very well, and plus the lift thickness is very large, but that's all right. And unfortunately, they got a failure. Now this sketch down below is just to illustrate how this happened. The scarp here is, of course, vertical and then goes down. And when they dug up the geotextile to see what happened, here's what they found. It had torn. And so what did we learn there? Well, it's got to be strong enough. That's the lesson. It's got to be strong enough. We do this calculation and we just make sure that we have sufficient strength in the geotextile going at the base of the embankment to take up that calculated stress. Here's another Corps of Engineers job somewhere in coastal Georgia. 3 rolls of geotextile laid out. This is the easiest way to install it, as you can imagine. Go across the swamp in this direction. You can see the dozer blade here. They're already bringing in fill. Here's a roll this way. Here's another roll out here in front, and then a third roll. And yeah, it's a soft site. That's one reason they got the fabric, was because they had the failure of that tractor. Came back Monday morning. All failures occur on weekends, of course. And here's the embankment had settled into the soft soil. And here's a classical bearing capacity failure surface, a Crandall failure surface. And here's on the Corps of Engineers is great because they tell us what happened. And here's the original design. Look at that, the 5-foot high embankment, nothing. And there are the 3 rolls of geosynthetics overlapped. And when they went and dug down, this is what they found. They just separated. How much interface friction does a geotextile have? I don't care which one it is. And in mud and water, not a lot. And of course, they just separated. What's the lesson? We have to positively seam any rolls of geotextile or any geosynthetic that we put out on a soft site. We've got to make sure those joints are strong. There's a lateral pressure failure that occurred in Hong Kong. Probably it looks like the embankment just spread laterally, and that's because you have horizontal earth pressures in that embankment, shown here schematically, and that has to be taken up by shear stresses at the base of the embankment. And that's one of the things that we design for. We have to have sufficient resistance, sufficient strength at that interface at the base of the embankment for lateral spreading. Now, we learned to construct, again, from the U.S. Army Corps of Engineers at these 2 sites, Pinto Pass, Mobile Harbor, Alabama, and Craney Island, Virginia, and I'll show you a couple of photographs from there. This is an aerial photo of the Pinto Pass dike. This retention dike was built in the late 70s, as you can see. 4 sections here eventually got a height of 25 feet, started out about 8 feet high, on material that you cannot walk on. I don't think you can walk on 3 kPa. It's about 60 psf material. You'll sink into up to your waist. So they managed to do it by very careful construction procedures that we'll talk about. Here's another big retention dike in Newport News, Norfolk, Virginia, where the U.S. Naval Base is. There's all sorts of shipping that goes out here to the North Atlantic, to Europe, and the Craney Island is a disposal site that the U.S. Army Corps they're obligated to keep this harbor free. There's a lot of sediment that washes in from Chesapeake Bay and all the rivers that come in there, and so they dredge the spoils out of here and dispose of it at this site. And you can see how big that is. There's a retention dike way over there. Somebody has tossed a standard ASTM 1 kilogram stone out there, and it splashes in the mud. And look at this guy's. There's the top up here, and he pushes that down in there. If that's wood, it's hard to even hold up because it'll float. What's he standing on? Geosynthetic. The Army Corps found that before geosynthetics, they started construction, they would dump in, this would be the displacement of it, about 60 feet of fill to get 10 feet of embankment. When they started using geosynthetics, the ratio became about 1 to 1, 10 feet of fill and 10 feet of geosynthetic and soil. And to make that embankment on that soft site, you have to have very flat side slopes. Here's the top of the embankment. You can see how flat that is. And there's the geosynthetic out there. And there are a lot of techniques on construction of these sites that we'll talk about when we get into construction. But we learned an enormous amount on how to build these systems on very soft sites from the Corps. So here's a break for questions. And Aaron, do we have any questions?
We only have one very basic question, and we discussed it before we started the presentation, and that is asking for a copy of the presentation slides.
No. Okay, good. Well, let's soldier on then. Excuse me. So let's talk about design, or at least introduce it. Now, I've got a note here. Soft ground stability is not the same as roadway subgrade stabilization. In the early days of geosynthetics, these projects were often treated as if they were roads. And basically, the consideration is the dead load versus the live load. If you have trouble supporting your dead load of your embankment at a site, you've got a soft ground stability problem. If it's live load controls the performance and the stability, then you've got a roadway problem. This slide shows the ultimate limit states of reinforced embankments. So we've got overall stability, and that's what we talked about there at Craney Island. We have to have very wide flat slopes or berms out here to take care of this particular failure mode. If you have a limited depth to firm bottom, you may have a lateral squeeze problem or extrusion problem, and I'll show you a photo or slide that illustrates how to calculate that. We could have rotational stability. That was the one that from the Virginia Highway Department, that failure occurred. A lateral spreading. This is similar to the Hong Kong case that I showed you. So the frictional resistance along the base of the embankment is critical. And if for very high embankments, you may have some stability problems in the embankment itself. Serviceability limit states are due to settlement. Good old Tertagi is working in these soft sites, and you're going to get a lot of consolidation settlement, and that could influence the performance of this structure, whatever you're building, a highway or a levee or whatever it is. And then we talked about the stretch strain, I guess it is, and deformation in the reinforcement at the base of the embankment. All of that has to be calculated. So design steps are shown here. We've got these in the notes in Chapter 7, Section 3. 3.2 is what we call the cookbook. It's basically a list of these things: do this, do that, do this next. And if you do these projects frequently, you don't need to look at the commentary. The commentary is there if you have a particular problem, because we didn't want the cookbook getting so long with all these side issues. And so we put those into this separate section. 7.3.3 has the commentary. And then there are these general factors down here that you have. And we'll talk about that when we get to construction. So I'm going to just look at these 5 through 11 are the critical analyses for reinforced embankment. The schematically 5, 6, and 7 are shown here. Overall bearing capacity, remember the failure in an embankment, the rotational stability in Virginia, and the sliding in Hong Kong. For overall bearing capacity, we use classical soil mechanics, foundation engineering for the ultimate bearing capacity of a shallow foundation. This is the classical Prandtl equation that was developed in the First World War. The allowable stress is the undrained shear strength, a bearing capacity factor, depending on the shape and the other factors that influence bearing capacity, divided by a factor of safety. That's the allowable stress, and that's gamma of the fill and the height of the fill. It's gamma H. It's classical soil mechanics. A few comments. Reinforcement does not increase the bearing capacity of the foundation soil, but reinforcement enhances the beneficial effects of these things. Limited thickness of soft soil. If strength increases with depth, just reinforcement helps you. If there's a dry crust, which is very common in sedimentary deposits, especially in glacial areas, that you have a dry crust from seasonal dry periods, berms and or flatter slopes are enhanced by the use of geosynthetics. And poor pressure dissipation if you have stage construction with or without PV drains. So if you have any of those things going on, the reinforcement helps you a lot. I had a PhD student, Dana Humphrey, who was just retired as dean at the College of Engineering at the University of Maine. And he did this thesis on embankments on soft foundation. And had this wonderful, all these case histories back in the mid-70s. And what he did, he plotted embankment height, did this in meters, versus undrained shear strength, average undrained shear strength, and plotted all these stable and failure cases. And this is essentially the bearing capacity line that you saw there, typical value. And what we found is there's kind of an upper limit of reinforced, safe reinforced embankments that perform very well up to about this limit. So a couple of examples. Let's say you have an average site of soft site with 10 kPa. That's really soft. It's about 400 psf. And you want to build a 2-meter high embankment across here, you probably don't need a geosynthetic. However, if you wanted to build a 6-meter high embankment, forget it. No matter what you do and how strong this reinforcing is, it probably isn't going to work. So this gives you a first shot at whether you've got a chance for using reinforcing at your site. And if you don't, if you want to build 6 meters, you may have to do it in stages. There's a lot of things you can have to do. change your construction procedures, and the time available. So this is a very useful preliminary design chart. Show you have half a shot at getting whether you have half a shot with the geosynthetic. Bearing capacity, I already talked about that. If you have limited depth to firm bottom, then you get a squeeze out at the toe, and plasticity theory is used for that solution. That's discussed in the commentary. There's a lot of additional information in there because this is a rather specialized case. We use berms or very flat slopes, as shown in this slide. So next is rotational stability. That was the classic case in Virginia, where the geotextile ruptured here because it was not strong enough. So this happens. Test embankment in Bangkok, and you can see here's the scarp, and here's the failure. Is the classical. Boy, if that doesn't look like that cartoon, then we just showed you. There it is. And calculations are shown here in this figure 7-3A. It's kind of a busy figure with a lot of algebraic notation. I'm going to show you this one from a TRB paper that I wrote with a colleague from Sweden. He invented this short sheet piles with a tie rod, and that performs exactly like a geosynthetic at the base of this embankment. So the factor of safety is a simple moment equilibrium. The resistance provided by the shearing stresses along the potential failure surface and the overturning moment. And here are these two items are the effect of the reinforcing. That's the contribution that adds to the resistance of the force. These forces are the same, so the forces tending to cause failure are the same, but the resistance is provided by the geosynthetic. And there's another example, figure 7-3, that shows a little more detail there. I like this cartoon from ground engineering in Britain. This is probably, 30 years ago or so. That if we can incorporate boundary elements, and well, you can read it. Statistical evaluation of parameter generation and stick to the fuzzy sets, we can get accuracy to at least the fourth decimal. Well, remember, the quality of your geotechnical investigation depends on the quality of your data depends on the quality of the geotechnical investigation. So here they are filling those scores because that's what the engineers want. And they're just using, I don't know how you're ever going to use this result to calculate the stability. Lateral spreading, the Hong Kong case. And we've got two cases that we go into detail, whether you have assume a cohesive interface or a frictional interface. But the same effect, you have slightly different equations. Limiting deformation was the 8th item that we have to worry about. And these are determined, these limits of geosynthetic strain have come about from field experience. Cohesionless soils from the Corps of Engineers, embankments, somewhere between 5 and 10%. If you limit it that, it'll probably work okay. If you have cohesive soils in your embankments, it could crack at fairly modest strains. And then the Canadians have found on peat foundations, somewhere between 2 and 10% seems to work. This is just empirical observation to keep the modulus of the geosynthetic stiff enough so that it's within this thing for our these values for our particular job. The Hong Kong case, lateral spreading, we talked about that. There's a new road that's, I think in upstate New York, it's already been patched, or let's say new has been repaired recently, and it's already cracking. So that movement is continuing. Longitudinal strength requirements in the longitudinal direction. And let me show you why that is. when we build these embankments, we cannot magically deposit all the fill clear across the whole embankment. So we're forced to build this in sections, and we put the geosynthetics down toe to toe, seam it in here. That's the seam strength that's really going to control, and then build the thing in such a way that we keep the stresses constant. So let me go back to that previous one. So the strength of the longitudinal seams controls stability. So we check the bearing capacity and rotational stability at the embankment ends. That we go back and look at steps 5 and 6, and so we know how to do that. We make sure that the strength and elongation from step 7 and 8 to control embankment spreading is okay. And then we choose the higher of the two strengths to control the transverse seam strength. So there you are. That's very important. So we check out the stability of these piles of sand, whatever you're using, to make sure that that seam strength is sufficient. Factor of safety. If you calculate at your site for what your embankment anticipate is, embankment that you want to build, you make sure, and the factor of safety is slightly greater than 1.11, 1.15, and you say, yeah, you know, it's probably okay. But your boss or your client wants you to have 1.5. Okay. How do you give them 1.5? You use a geosynthetic reinforcement at the base embankment. And you can, with confidence, tell them, yes, factor of safety now is 1.5 or whatever they want. If you make the calculation and you find your factor of safety way, way, way less than 1 without the geosynthetic, you got a problem. The geosynthetic enables that construction to take place. And emphasize here, geosynthetic must work. And that's what we have to make sure that it's strong enough and so on. So are there any questions about design? Aaron?
We do have 2 questions here, although I don't know if they're specifically related to design. I'll let you decide. You're the expert. So the first question is, will there be differential settlements between the reinforced zones and retained zones in a GRS built on soft soils?
Probably. I think that depends on the construction process. For embankments, the geosynthetics goes toe to toe, as I just showed you in that last slide. So we don't have that issue of retained fill. You do in walls and slopes. And so I don't know if that answers your question, but yes, I think you will have differential movement there between those two sections. That gets into the wall business. It's a little bit different than what we're talking about in this lecture.
Great. There's another question. When should FEA be used versus conventional design methods described here?
I guess it depends on how good your subsurface investigation and your laboratory testing are. If you have confidence that your properties are just the absolute best you can obtain, that you spend a lot of money on subsurface investigation, the highest quality piston samples, and high quality laboratory testing, then you can probably do a finite element analysis. The big problem I found with doing fancy finite element analysis or finite difference analysis is that you get a lot of pretty pictures, and so you tend to kind of believe that your answer is correct. Always check your solutions with these hand calculations or very simple programs. Always make sure that you're in the right ballpark, as they say, but not even worrying about the ballpark, whether you're playing the same game. And it's so easy to get fooled with by modern numerical techniques. So if you check your design and you have high quality input information, sure, love it. It's great.
Great.
Anything else?
Let's proceed for now.
Okay.
Oh, wait, hold on. I'm
So
sorry. One more question just came in, if you don't mind.
Okay.
Let's see what it says.
Let's try it.
Does this design approach consider the behavior of expansive clay, in parentheses, bentonite? Is there any comprehensive design guide or specification that is being used for this presentation?
No, I'd say not. Typically, soft sites don't have expansive materials in them. And so it's never been an issue in embankments on soft ground. That is an issue, say, for highway construction, road construction, and so on, where the roadway now is subject to those climatic changes that lead to expansive soil problems. But not in this case. These soft sites, it's compressibility and stability, not expansive soils. So I hope that answers that question.
Okay. Yep. Feel free to move on.
Okay, now let's talk about material properties and test methods. This is where we get into the geosynthetics. Soil properties, as usual, you want to use the highest quality techniques that you have available, the latest technology, the best highly skilled crews for taking your samples, the best laboratory tests that you can perform. Whatever you can afford is so important for these sites. If you don't have that, if you're just using SPTs or something out there, you've got to be really, 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 really careful. And this is my best soil it's site investigation slide. I love this. You always stick your head down there and see what the soil's like. Any questions about soil properties? If you send me an email, I'd be glad to give you a couple of references, including an undergraduate textbook that tells you everything that you want to know about soil properties. Geosynthetic requirements. See this table 7-1 on page 725 are listed here. Design tensile strength. We already talked about why that's important. The deformation at failure. The modulus at the design strain. Soil geosynthetic friction. Creep. I've got double question marks here, and when we get into discussing these in details, I'll give you some suggestions about that. Survivability and workability, drainage and filtration, and the seams. So for tensile strength and modulus, we use the wide width test. Ideally, we'd like to determine this in soil, but practically speaking, we use the ASTM 4595 or 66737 for geogrids. And this shows the wide width clamps in our lab, 4 by 8 inch or 100 by 200 millimeter specimen, to try to take into account the strain at the edge. It's not quite perfect. It'd be better if it was wider, but it's a practical thing. And that's why I said here practical. That gives you a pretty good handle on the tensile strength of the geotextile. Note that many, especially woven geotextiles, are used in embankment reinforcement, often have different strengths in the machine direction versus the cross machine direction. You've got to make sure that both directions are tested so that you know what you have and that the geosynthetic can be put down correctly in the field. And then I show this biaxial geogrid down here. It's not that easy to clamp those and get the correct tensile strength. Always test the seams. We're going to see this slide later. We get to construction. It failed. Here's the organic material from the swamp coming up into the fill. You can tell they've already got this here. Repairing that is really, really difficult. You'll probably have to waste all this fill, waste this geotextile, and so on. But testing seams is not easy. This is a very high strength woven geotextile, multi-filament woven that has, you can see some of the threads across here and here. With roller clamps, this is in Barry Christopher's laboratory, very, very difficult to test. But you've got to do that because you don't want this to happen on your site. Direct shear tests, we use the ASTM 5321 or pull-out 6706. They probably are okay, but the pull-out tests, I say if you wanted, well, I'm not real happy with the interpretation that's suggested in 6706 for pull-out tests. Creep, I've got double question marks because I don't think it's a problem in most cases. Once you get to the end of construction, it'll settle, but your factor of safety increases with time as the consolidation occurs. However, I've got double question marks there because there are some soil deposits, especially in Ontario and probably in Quebec, that where the creep occurs in the geotextile even after the end of construction. So long-term creep, it's some kind of a secondary effect. If you have that problem and you think you have that problem, see the lecture that was given at the Rio Conference, Geo Americas 2020 last year by Professor Kerry Rowe. He has measurements on these and tells you how to take care of this particular problem. But it's a rather specialized soil deposits. Most of the time, estuaries and the soft sites that we've dealt with, you don't have problems with that. Drainage and filtration, I'll refer you to chapter 2 in our manual for a very good, simple design procedure. Survivability and workability, I've referred to a couple of earlier Federal Highway publications. Settlement and creep, we're talking about the rate of settlement of the embankment versus the creep rate of geotextiles, and I've already mentioned Kerry Rowe's work on that. That's a very good reference. Geosynthetic survivability, it depends on the subgrade conditions and the construction equipment. And we have some recommendations for that. If you have a site like this and you're going to try to deploy your geotextile or geogrid across here, it's got to have high survivability properties. Otherwise, it isn't going to survive. If you get out to the site and you've got a working table like this and it's all ready for geosynthetic, the stresses that are active on that geosynthetic are rather modest. So it depends on the subgrade and equipment, the cover material and equipment, crushed rock or rounded sand, fine sand. Properties of the geosynthetics are shown in tables 7.4 and 7.5. I have put into this box down below here an important geosynthetic concept. A geosynthetic cannot perform any function unless it survives insulation, aggregate placement, and initial traffic. And I don't care if you're talking about a retaining structure, filter, erosion control, highway construction, or whatever. It's got to survive the initial installation, aggregate placement, and whatever the traffic is. And traffic, construction traffic, and that sort of thing. We're lazy, and construction workers are just as lazy as we are. And so I tell this dozer kind of move this roll around. Well, look what is that doing to the first 2 or 3 or 4 layers of geotextile? I can tell you it's not doing it any good. And the same thing here. Here the operator's looking down and whoops. And what's this guy doing? He's looking the other way. He's probably an inspector. If this is your representative out there on the site, he needs to tell the operator, don't do that. And in fact, this is ruined. It should be in your specs that geotextile has to be taken up and disposed of at the contractor's expense. This was a test that we did at one of the very early sites in Sweden. The Jihan showed you yesterday photographs from. This is the geotextile, a test that we did, and yeah, it punched holes. At that time, we thought, well, that's pretty good. Well, I'll tell you, on a multi-filament woven, it was not very good. And this is placing a riprap with a maximum drop height of 1 meter. Yeah, that's what you often see. And you have all these guys sitting around talking about sports and the weather and not doing their job. I like this one. This dump truck is placing fill, and rather than drive around here and drive on already placed gravel, they drove this way because it's a little shorter. And of course, those tires are not doing the geotextile any good. I love this. Unfortunately, this cradle arm is dragging the geotextile along here. You can imagine what that's doing to the outer layers there. And this one, look at this guy. He's driving right out on there. And here's a picture of him. And you got 1, 2, 3, 4, 5, 6, 7 folks standing around, including the operator, that there's no reason why he can't spread his fill from the already placed material. And if you see this happen, somebody here has to tell them, don't do that. That's not good. Stiffness and workability is the ability of the geosynthetic to support workers and construction equipment, called its field workability. If you walk out on site and you can see the boot prints coming down here, and this fabric is not stiff enough. It doesn't have very good field workability. This guy's really struggling to get this fabric placed out on this soft site. Not very good. Or this is going to take up tension. They're already placing fill, as you can see. And look at the condition of the subgrade here. It's terrible. And so this is going to take a lot of strain before it starts to take up develop any tension in the geotextile. This is a reinforcing job. This is not good. And similarly here, you can tell the stiffness of the geotextile. Whoops, I didn't want to do that. There we go. So there's a design example in the chapter. This is one of Barry Christopher's projects. It's got a lot of detail in there. You can follow that. It follows the steps that we've already talked about for design. And goes through the example to show you how to do it. And we've got specifications. Very reluctant to put those in for the simple reason that I don't want you copying those. And I know most engineers hate to read specifications and boring and so on, and yet it's absolutely essential on these particular projects that you thoroughly familiar with the specs. Don't just copy these verbatim. Some topics here are pretty good. It's not a bad outline, but don't copy the specs verbatim out of this manual. I can tell you the contractors will have attorneys reading those specifications to find loopholes and places where they can claim extras or that they see are problems. So any questions about soil and geosynthetic properties before we get into our final section?
No new questions at the moment.
No new questions. Okay.
Maybe pop in a few seconds as people type them.
Yeah. One thing I should mention, everybody, I put my email address there. I'll be happy to try to answer any questions that you may think of later. And also, if you want a copy of my slides, I'll be happy to send them to you. It's a big file, as you can imagine. But if your email can take that, I'd be happy to send it to you. So let's talk about construction. This is a key to the success of especially very soft ground construction. We're going to talk about, mention pre-construction meetings, equipment selection, site preparation, geotextile placement, and then fill placement. So I don't have any slides that illustrate pre-construction meetings, but this is important. Try to get, if your agency or your client will agree, a meeting with potential bidders for your project, contractors that do this kind of work. And you tell them what some of the things are about geotextiles, about sewing, the type of equipment they're going to need, the rate of fill placement, and so on. You want contractors that have confidence they can do the job. That's really, really important. And so sometimes pre-construction meetings, you separate the girls from the women. The people that say, oh, that can't be built, well, good. Get out of the room. Sorry I wasted your time. But you want contractors that believe they can do the job, that have the proper equipment, and that have the confidence to make the construction that you anticipate. So if they have the confidence they can do it, it makes the couple of hours that you're going to spend describing the project and talking about all the problems that you anticipate. Very, very, very worthwhile to get contractors that have confidence that they can do the job. So let's talk next about equipment selection. This is not a, if your contractors are highway contractors, they've got to have special equipment. A small dozer here with very wide tracks and a small blade, they're not going to move a lot of fill. It's not going to move cubic yards per hour because they're working slowly on thin lifts, very small contact pressure, low contact pressure for soft site. It's the only way you're going to get that kind of construction. One of Barry Christopher's jobs, I think the one with that case history is the contractors purchased this kind of equipment, which is used by farmers in the agriculture industry for depositing very thin lifts of fertilizer. And it's got a gate on the back, of course, and then this blade pushing the material out. You see these wheels are offset a bit. You got a tricycle steering gear, and so this is used by farmers so that you don't compact the soil around the roads. And it's perfect for this kind of construction. You want a 15 or 18-inch lift. This thing can drive down the grade and push they can control the lift thickness. It's very, very effective. A working table is usually not necessary. If there's a dry crust, which often occurs, or a vegetated root mat at the surface of these sites, don't remove it. Highway engineers often, they want to take away all that organic material, excavate. Minnesota Highway Department, I worked there as a student, and they took out the top 3 feet routinely because it was organic or had roots and other vegetable matter in, is going to affect their highway. Well, we want to take advantage of those things. Don't remove the dry crust. Make sure the root mat, the vegetation remains, because it is a little bit of extra insurance for your project. Use a high survivability geosynthetic instead of a working table. That will, usually that's not a problem, but just make sure. And a geosynthetic reinforced access roads may be required. Bringing the fill in on the access road, there's several advantages in doing that. But if you have a very soft site, you may have to have reinforcement on those access roads as well as for the main embankment. So here's a roadway going across here, or fill, I'm not sure what this was. Here's a soft site, as you can tell here. Here's the root mat, or the vegetation growing there. And they just roll the geotextile right out on that and are spreading the fill right on that. And there's nothing wrong with that. This stuff is going to get below the water table. It's going to be protected. It's not going to, the settlement that you're going to get from its decomposition whenever that doesn't take place is modest compared to the settlement you're going to get on due to consolidation of the soft soils. Placing the geosynthetic, you want to make sure you connect all seams. If geotextiles, you have to sew them, and if geogrids, you use bodkin joints. We have tried for 30 years to find a way to connect geotextiles without damaging the geotextile itself, reducing the strength. The seams are always weaker, and that's true with geotextiles. The sewing breaks threads and punches holes in the material, so the seams are always weaker than the intact material. With geogrids, you have to use bodkin joints, and I'll show you some cartoons of those. You want to place the material fairly flat. You probably will have a mud wave developing for the first lift of soil on very soft sites. Take advantage of that mud wave. You can work on it, and if you have a stiff fabric, that workability may determine the rate of placement of the geotextiles. So if you have a proper selection of a stiffer fabric, you can take advantage of that mud wave, but it has to be controlled, as I'll show you. So geotextile overlap instead of seams. This is a soft site near Seattle, and sludges. That was the mark where the seam was originally, and this is you can imagine it coming out towards you, the mud wave, this rounded area here. And, they didn't want to, the owner didn't want to, and the contractor, I should say, didn't want to sew it. And so that's what they have. Here's sewing, the handheld sewing machines. It's a modest amount of sewing, that works fine. It's kind of hard work. And so a lot of times, especially heavier sewing machines that use a winch on a little golf cart kind of thing to transport the thing. This is hard work. These are heavy machines. It's hard work. And you do need people there to provide it. Here's the sewer, here's this driver, and two guys holding the geotextile getting ready to sew it. You probably don't need all of these people sewing, but here's the sewer, this is a helper, there's a helper. And one of these people needs to be the inspector, where they take a ballpoint pen or an awl and inspect every seam. You want to make sure every seam is inspected. When the machine is right here, the person describes checking out here and they find the missed stitch. It's easy when the equipment is still here to go back and re-sew that. It's too late if it's buried under 6 feet of fill. This is a good seam. It's about an inch from the edge. This is obviously a woven, multi-filament woven. You can see the 2 rows of stitches there. You want to be far enough away from this because this will unravel, as shown here, or unraveled, and that seam is not going to transmit much load, as you can tell. This guy's using electrical sewing machine and water. I think that's pretty risky. I don't like that, but he does have rubber boots on, so maybe he will not get electrocuted. Here is a site, not sure where this was, but the geosynthetic was sewn off-site and then deployed. As you can see, they're bringing it out here on a work table. And here's one seam up and then two seams down, one seam up, two seams down. So it had it folded in such a way that some of the seams were down. And somehow, one of the down seams was found. And notice that the seam is down. And how did that? That was really dumb luck. I'm surprised the contractor didn't cover that up real fast. And that's the problem with having seams down. They can't inspect or repair. How do you repair this? You have to pull all this geosynthetic up and try to, or sew a patch on here. It can be very difficult, very costly, very expensive. Don't let that happen. So inspect all stitches. Geogrid. Geogrid here being deployed here with overlap on a geotextile separator, and they're relying on the interlock between the provided by the gravel in those. That's fine if the deformation is not very large. If you have a large deformation, you're going to get a mud wave, then they'll separate just as easily. Maybe not quite as easily, but it'll separate. So you have to use a bodkin joint, bar like this, a PVC bar, PVC pipe, cables, electrical clamps. There are all sorts of techniques that have been used to clamp these two layers together. So that's woven through the openings in the geogrid. And if you need to trim the length of the rolls, make sure this guy is wearing safety glasses. A lot of hot plastic flying around. Here's the seam that was missed. This is that same job that I showed you near Seattle with the mud wave. There's the pin in there. A couple hours later, it had spread like this. By the end of the day, it was like this one. And you can see it's just separated now. This is all waste. That's the sludge that we're trying to prevent developing. And so now you got a problem. You have to bring this patch in, as you can see. Hope it works. It's really too bad. Somebody missed the stitch inspection, and they should have caught that before it was installed. Geosynthetic placement. In this case, they're rolling down along the center line rather than transverse. That's fine if you either seam here in the center line or the deformations are far too small. You may need a lot of people pulling out the geotextile, deploying it, but I don't think you need this. I don't understand how they even could do this. It's a little silly, it seems to me, but this may be necessary, and that's fine. Now, the rate of geotextile placement depends on its ability to support the workers. That's what we call the workability or stiffness of the geotextile. I showed you that one earlier. Lost an inspector here, right down to the bottom. Well, actually, what happened, you can see the fill being brought in here. It was a test. They told the operator, or told the driver, not more than 3 feet of fill. And of course, he pulls the lever on his dump truck, and it goes up, and it's a pile about 7 feet high, I'm told. And I was standing there for about 30 seconds, and then right down to the bottom. Don't let that happen to you. If you want one of the things you can do, and I'll show you that, you place off on already placed soil fill, and then bring it in with equipment. So placement and compaction of the fill, use low ground pressure equipment. I already showed you photographs of that. Cohesionless fill, at least for the first few lifts. I would like, if you have problem getting cohesionless fill and you want to pay for a lot, maybe a first 2 or 3 or 4 feet of fill would be cohesionless to permit. It's just easier to construct and reduce the stresses on the geosynthetic, and then you can build an embankment out of whatever you want later. So the rest of the embankment. Keep a U-shaped leading edge, as I'll show you here. Here is a mud wave with the fill coming out. This is one arm of the U. Stage construction may be required. As you can imagine, the load is the highest there in the middle, so you have the greatest settlement here. And that's not very good from the serviceability point of view. So, but there are ways that we can do this. You can build this thing instead of just in conventional layers, is to build it in sections. So you have the geotextile at the bottom, and these access roads over here to kind of anchor it and stretch it, and then that can be used for bringing fill in to fill in the sections 3 here. And you see what that's doing. It's keeping that the stress on the geotextile the same, building the embankment the rest of the way up. So the geosynthetic reinforced haul roads here at the edge. And this is now what I talked about, the U-shaped, let me go back here. U-shaped leading edge. Dump the fill on already placed fill. The dozer operator keeps these 2 arms the same elevation and the same distance. And if he does it right, it stretches the geotextile, puts the geotextile into tension. And this is the direction of the construction. So you fill in this and do it very gradually and very, very carefully. This is if you anticipate a mud wave with very soft soils, not just put a couple of measures of shear strength for the soil. For a very soft site, that's usually where we're going to get mud waves. Here's the geotextile the geotextile deployed. Here comes the dozer just pushing out. Notice this guy's the driver. He's stuck. Okay. But look at, he's bogged down. It's about a foot or more there, and there's no reason why he has a full load he can't deposit up here, or if he has to got to drive out there and have half loads on his truck. And these guys are sitting out here smoking cigarettes at their dozers. There's no reason why you can't put them to work. You dump out here. The drivers have here. These guys are putting them to work to spread the fill, like it's shown here. Same thing here. This truck is too full, and he got stuck on the sand. And you've got this dozer and this dozer here. Put them to work. And here they are going out. They're just starting out, so they're having trouble getting this into tension, but they'll figure it out. And here's one arm of the U, the other arm of the U. You can see the mud wave developing here. Do that carefully and in a balanced construction. It will tension the fabric. Now we get to the end of the swamp. Here's one arm of the U, another arm of the U. Here's the bottom of the U. Looks like no matter what they're doing here, having a contact, you're trying to decide what's going on here. And clearly the soils are stronger and maybe shallower. The mud is getting thinner and thinner, and that's what happens. So just reverse the U. So now the bottom of the U is this way, and the arms are down here, and that'll stretch so those wrinkles will be pulled out in advance of construction. So this will stretch that out if it's done properly. And my experience with dozer operators is that they love to do a good job. So I would tell them what you want, show them what you want, make sketches, make sure they understand, and they'll do a good job for you. So, any questions on construction? Aaron?
There are a few questions that have come in over the last 15 minutes or so. I also want to note that we
Good.
have about 15 minutes left of our presentation time.
Good.
So I'll start with the first question, and it's a simple one. Well, probably not simple. It's a short one. Can clay soils be used as backfill on geosynthetics?
Well, I'm not sure what your application is. If you're talking about embankments on soft ground, I think it's a good idea to have the first few lifts to be sand or granular materials because they're easier to compact. You get a lot less compression in the embankment itself, and you don't have stability problems. And for at least a few lifts of the embankment. Beyond that, I think you can use cohesive soils. If you're talking about cohesive soils and geosynthetics, I've never been a fan of that. I think that yeah, it probably will work, and some retaining structures they've used clay backfills in climates where you don't have a lot of rainfall and everything's dry, but I don't know. I like to avoid it, and I know that on-site materials it's very tempting to use. I can tell you many cases of failures where they used on-site materials that were inappropriate. So unless there's a huge compelling economic interest, I would recommend you use at least in the vicinity of the geosynthetic granular materials, free-draining granular material. Anything else?
Okay, here's another question that's more of a general question. Is there any global map or database on the use of geosynthetics in the construction industry based on geography, weather and climate, or even cultural or socioeconomical backgrounds?
You know, I not being in that part of the industry, I would recommend you contact Fred Chuck at GMA, one of the sponsors of this conference, or even any of the people that work in the industry that should be able to tell you some marketing data and some of that sort of thing. Those to answer that question. I'm sorry that I'm not a marketer. I'm an engineer and a professor, or at least a former professor. So I can't answer that. I usually rely on industry people to tell me that information. So I'm sorry, I'm not fluent in that subject.
Okay, we've got another question here. Let's see. During construction on extremely marshy soils, should a temporary working platform be constructed for equipment access, such as rigs for installing drains, etc., or a stage-wise embankment construction? Actually, I'm sorry, I don't know if I understand this last part of the question. Let me read it again. During construction on extremely marshy soils, should a temporary working platform be constructed for equipment access, such as rigs for installing drains, etc.?
Probably you'll have to do that. Yeah, and they may require geosynthetic reinforcement. If you want a working table of, say, 1 or 2 feet, and your site is so soft, you've done all the things that I've recommended. Don't take the root mat out. Take advantage of the dry crust. Deploy it. Your geotextile out there. Sew it properly, and so on. That if you still can't support that working table thickness, and you will require a decent working table thickness to be able to operate a crane for installing drains and so on. Then you will have to design a geosynthetic reinforced embankment, or getting it to even construct your working table. There are sites where you have to do that, and they require some real good subsurface information and some real good geosynthetics information and so on. And if you can manage to do that, my hat is off to you. Write a paper on your success of your project, because that is not easy to do.
Okay, well, let's go ahead and move on then, since we've got about 10 minutes left. Sorry, I mean, no more questions at the moment. We got about 10 minutes left until the presentation time ends.
Well, let me just summarize what we did today. We talked about conventional solutions to embankments on very soft foundations. I had a list of, I remember, 9 or 10 possibilities for a soft ground embankment. A good engineer will consider all of those, and you may decide not to do some of those soft foundation soil improvement methods because you don't have contractors available to do them, or you don't have equipment, or nobody knows how to do grouting or do stone columns. They don't know how to do all that stuff. If you don't have contractors that can make that construction and understand the problem, you're barking up the wrong tree. It's just not going to work. So then we talked about geosynthetics applications and early case histories. Those were important because they had lessons for us on how to design and construct these systems. They're critical, important, difficult projects. And we've learned from those early practitioners that were willing to tell us how they messed up and what mistakes they made. The Army Corps of Engineers, Virginia Highway Department, I'm really, really thankful for their frankness and willingness to tell us what they did wrong. So that was the first part of the presentation, is those early case histories and the lessons learned. We went over design concepts and design details based mainly on the information in Chapter 7. And I commend that to you. If you have one of these projects, study that chapter. You can get into some of the details in there. There's a lot of information, commentary, specialized material. And if you do these projects rather often, that checklist there, the cookbook part, is important, just to make sure you covered all bases. That's important in any design of a complex system. Don't forget about the soils. There's a question about finite elements. Well, that's fine if you have good soils information. If you're using an SPT and then correlating to get modulus and things like that, and I've seen that done on projects. My God, that crude test, and you're doing some correlation that was developed in 1950 for modulus. I mean, that's crazy. And yet, I've worked on projects, usually failures, where fancy finite element analyses were done, and garbage in, garbage out. Remember the two guys filling the cores for the lab in Britain? And then we talked a lot about geosynthetics testing, because this is a geosynthetics conference, and geosynthetics are important. And how we get those properties, ASTM has done the profession wonderful, wonderful service in providing standards for determining the test for the material properties. When I started in this business in the early 70s, I can tell you, I looked at the ASTM. There was nothing on geosynthetics. There were all this stuff on carpets and curtains and kids' pajamas and everything. And none of that applied to what we were trying to do, which is geotextiles in those days, in the early days of geogrids, in highway construction or in embankment construction. And so I really hand it to ASTM and D13 for having done such a fantastic job in the Geosynthetics community. Sorry, it's D85. It used to be D13. D85. Or sorry, D35. They've done a fantastic job for us. And finally, construction. Those procedures. I've got a long discussion in the chapter on construction. A lot of the things that I showed you quickly on these slides are very important, are crucial for proper success of an embankment on soft foundations using geosynthetic reinforcement. And let me go one more. So if you have any other questions, there's my email address. It's a very simple email address. Be happy to send you my slides and be happy to answer any question that you might have. Just tell me that you're a participant in this session, and I'll do my very best to get back to you. I may not get back to you today, but I will as soon as I can. So with that, I thank you very much for your kind attention, and the questions that I did get were very good. So thank you. Aaron, I think that's it.
Great. Well, as you mentioned, if there are any other questions, folks can email you. So with that said, we'll go ahead and close out. Thanks very much, Bob, for the session today.
And thank you, Aaron, for all your help in getting me to do it the right way. So,
you're very welcome.
cheers.
Everything went very smoothly. Take care, everyone.
Yeah, thank you. Bye-bye.